Hello everybody, and thank you for joining us for the fourth talk as part of the virtual Primate Conversations seminar series. Today we are really excited to be welcoming Laura van Holstein, who is a PhD student in biological anthropology at the University of Cambridge, investigating mammalian models for macroevolutionary processes in human evolution. Back in March, Laura's work with her supervisor, Professor Robert Foley, on the importance of mammal subspecies in evolution, published in Proceedings of the Royal Society, made the national mainstream news. Laura has also published many papers on her project, and she has an exciting forthcoming popular science book called The Pigeonholing Species: How Humans Categorize the World, which is due for publication in 2021. Today, she will be presenting to us on determinants of speciation in human evolution. If you have any questions for Laura, please feel free to write them in the chat and I'll ask them on your behalf at the end of the talk. Thank you again, Laura, for joining us today, and we very much look forward to hearing your talk.
Thank you so much, Sophie, for that introduction. It feels really strange to be hearing all these things about myself, because I kind of have this image of myself of just, lurking in my living room for about 20 hours a day during this lockdown. It sort of feels like all those things happened to me in a past life. I hope everyone that's listening is doing well. I'm quite sad not to be in Oxford, actually. I know you're not supposed to say that as a Cantab, but it's mostly because I know you guys always have a really excellent selection of coffees and teas at the Primate Conversation. So I kind of brewed them up myself, and I have a selection of drinks of various strengths depending on how the talk's going. But thank you. So thank you for that introduction. Thank you also for the invitation to give the talk in the first place. And I have to also kind of extend thanks on behalf of the people I live with, because this gives me an opportunity to talk to somebody else about my research. And that's really all I've been doing for the past 6 months or so. I'm in the process of finishing the PhD, so this is really all I'm thinking about. But to kind of give you a bit of background or a bit of context for this talk today, the overall topic of my PhD, as Sophie mentioned, is mammalian models for evolution and kind of applying them to hominin, or to the hominin fossil record. And more specifically, I'm interested in the relationship between microevolution and macroevolution, which of course is a very old question. And I'm interested in how basically the within species processes scale up to produce the macroevolutionary patterns that we see in the fossil record. And so I'm applying that kind of thinking to the human fossil record today in this talk. So I don't know about you guys, but I tend to lose concentration about halfway through presentations on Zoom. So, God forbid it happens to me today or to you. But if it does, I wanted to give a bit of a condensed version of my talk here. So here's the talk kind of distilled into a very strong, almost alcoholic spirit. So it's also kind of to get a sense of where we're going in the talk, of course. But really the talk is focused on two main points. The first is regarding methodology. And I'll try to make it not very boring. And essentially what I'm going to try and do regarding methodology is to try and convince you all to be as much of a tree hugger as I actually am. And what I mean by that is that I want to kind of explore and show the potential uses of phylogenies as sources of data in our field. And basically the point there is that the way phylogenies are used in human evolutionary studies, well, first of all, they're not published very often. The last whole clade phylogeny was published in 2016, and so it's a little bit out of date. I mean, it doesn't include some of the more recently described species, but it also only makes use of cranial data, when of course we also have genetic data from the later hominins that could be included in a phylogeny. So they're not really the main focus of paleoanthropology per se. And when they are made, they tend to be the kind of be-all end-all in a paper. So rather than using them as sources of raw data, they're kind of just used to look at the phylogenetic relationships between species, which is fine. But I want to make the case that you can use them for more than that. And essentially what I want to do is I want to use the phylogenies to re-examine kind of old questions about human evolution, and to show you that's a useful thing to do. And there's two main reasons for that. The first is that with a phylogeny, you can actually measure things directly rather than just using proxy data. And the second, and that relates more to the content, the answers to those old questions, to me have actually been a little bit surprising, and not what I expected based on previous work. So really, it kind of feels a bit like, the Wild West, kind of unexplored territory, but that makes it quite exciting. So one of the oldest questions in evolutionary biology generally, and of course we're a subfield of evolutionary biology, is why does evolutionary change happen? And broadly speaking, answers of that question kind of come in two flavors. And if I'm allowed a generalization, well, one generalization in this talk, I'd like to make use of it now. So those flavors are basically biologists and geologists. So on the one hand, on the left there, you've got the Red Queen model, which sort of emphasizes biotic interactions between species as the principal force that shapes evolutionary change. And so other species basically control macroevolutionary dynamics. And the imagery there, of course, is of the Red Queen telling Alice that in Wonderland, in order to keep still, you have to keep running. And that's exactly the view of the biologists, is that in order to keep your ecological place, you must constantly evolve. And it's kind of, I think of it as a bit of a PhD model, because you're constantly running to, coding actually, to keep the thing going. And then on the other hand, we've got the court jester model, in which evolution doesn't really happen unless there's a change in abiotic circumstances, and those abiotic circumstances cause an upset in an equilibrium. So the image there is, of course, of the court jester kind of upsetting the day-to-day business of court. So some examples from the kind of wider literature to set the scene here. The classic image of the Red Queen is actually the predator-prey relationship. And I chose this picture of the T-Rex chase. I don't really know what the other species is, but chasing its prey. I chose it for Andres. I don't know if he's watching, but I'm a big fan of his paleo art, so I feel like he could have drawn this. But of course, the Red Queen element of that is that there's a selective pressure exerted on the prey to keep running faster, to evade the predator, and in turn that exerts an evolutionary pressure on the predator to run faster. That's a simplification, but that's kind of the model. Another example would be, and I see this all the time in my backyard, is brutal fights between dunnocks and robins that are fighting over the same resource. So kind of, I guess, batting for the Red Queen, we have birds, reptiles, marine species. They all show things like density-dependent speciation, where essentially speciation is controlled by the number of species that are already in existence and are competing for the same niche space. Then on the other hand, we have, on the court jester kind of side of things, we have the classic defenders, Verba and Gold. The example, of course, being the extinction of the dinosaurs. So the T-Rex can run after the other guys as much as he wants, but as soon as you add an abiotic factor into the mix, the asteroid, it's game over for everyone. So yeah, both these models have been invoked to explain speciation as well as extinction. And in fact, the original Red Queen paper was about extinction and not speciation. But what I'm interested in this talk is, and what I'm just going to focus on, is speciation. So when it comes to hominin speciation, the majority of evidence is in support of the court jester model. And it goes all the way back to people like Raymond Dart with his savanna hypothesis. You've also got Verba's turnover pulse hypothesis, where the origin of Homo is linked to climatic fluctuations. Your very own René gives evidence to support that point in some papers of his. And then we've also got, more recently, Matt Grove, who basically links speciation with climatic variables. And then sort of doing it for the Red Queen. So you have your René and I have Maya Robb, who argued even before I was born that speciation is not related to environmental variables. But of course, that paper is a little bit old. The Red Queen also tends to be examined from the perspective of kind of competition between hominins and carnivores, but those papers are a bit old. I think a brief synthesis and a fair point to make here is that overall, the climate model does have more evidence in favor of it. I'm not sure if that's because it's been examined from that lens or through that lens more, or if the sort of biotic interactions have been examined and the model has been found wanting and the results have just not been published. Now, it kind of looks like I'm dissing the entire field by calling everything a fad. What I mean here is that what all of these papers have in common is a reliance on first appearance dates of fossils as proxies for speciation. Now, I'm not actually here to criticize the approach, but there are obvious concerns with using first appearance dates. And a very obvious one is errors in dating or uncertainty around dating. But for me, the most important thing is that a first appearance date is not actually a speciation event. Actually, an analogy here would be that a crazy lunatic, which would be time or fossilization events, have kind of taken a chainsaw to a branch, which represents a species, and then we just randomly find one of those pieces and say, ah, yes, the origin of the branch. And what I want to make, what I want to argue here is that we should use those pieces of wood to essentially reconstruct the shape of that phylogeny, and then use the shape of that phylogeny to pinpoint more exactly where the speciation events actually happened, and how that varied through time. So that's what I want to do in the first bit of the talk, is to kind of reappraise this question of biotic versus abiotic forces shaping human evolution, but by directly measuring speciation rate rather than using a proxy for it. So the question here is, do we see either of these patterns in hominins? Speciation rate, I hear you ask. The way I calculate speciation rate, I'll go through this quite quickly, but I essentially use two phylogenies, although I'm in the process of making a third sort of consensus phylogeny with Rob, that sort of uses more, includes more recently described species and includes the genetic data as well. But yeah, I use these two phylogenies. They're actually based on the same data set. It's a cranial data set. And the only difference between them is that the one on the left includes ancestor-descendant relationships. And they're things that I think fossil people will find quite canon and quite widely accepted. So it's things like Anamensis being ancestral to Afarensis, Heidelbergensis being ancestral to Sapiens and Neanderthals, that kind of thing. And actually, because they come from the same data set, you can compare them. And the one on the left does actually have better statistical support. My overall approach has been to do my analysis on both of these trees and to sort of compare results between them to see how much they differ based on this phylogenetic uncertainty. But I give the one on the left kind of the benefit of the doubt, essentially. And the main conclusions, by the way, are exactly the same between these two phylogenies, so that's okay. I'm only going to present the results from the one on the left just for time. Yeah, so what I do is I basically, for both phylogenies, I slice the tree rootward, so that's in the direction of the last common ancestor, at 500 million year intervals, and I do it at 500 million year intervals because that's quite a good time range for speciation is kind of expected to take that amount of time. And then for each of those new slices, I calculate something called TIP-DR. Now, TIP-DR, it was first published or invented by Yates et al., and that was on a phylogeny of birds. And it's basically a tip-specific, so for each individual species or tip on a tree, you can calculate speciation rate for that species. And I do this on each slice for all of the extant species on that slice. Now, what this approach allows you to do is, and what I like about it, is that you can include ancestral species that we logically know must have existed, but we don't have the fossils for. So we would never include them in a sort of a FAD or a FAD analysis. So it's things like the common ancestor of all paranthropines. We know that it must have existed, but we don't have the fossil. But we know it must have existed, so you might as well include it in your data set or in your calculations here. So I think that's one of the points that I like about using phylogenies here, is the use of the ancestral points, but also that you can measure directly speciation rate through time as if you were there. So if biotic interactions played a bigger role in shaping hominin speciation, we'd expect to see a correlation between speciation rate and the number of species. And on the other hand, if the sort of external forces played a bigger role, we'd expect to see a correlation between the speciation rate and climate. And for climate, I'm using two types of data. I use benthic oxygen, which is it's more of a measure of global climatic conditions, and also aeolian dust, which is more specific to conditions in Africa. So results, they're quite surprising. There's no relationship between speciation rate and either of the climate variables, and species richness, so the number of species, is a strong predictor of speciation rate, and this is for hominins as a whole. So this is completely different to what we expected based on the sort of literature review that I did at the beginning. Now, if you were the court jester and you wanted to make a sort of legal case for defamation, you could do it on the basis of the problem of scale. And the argument would be as follows: this axis shouldn't really be horizontal, but rather vertical. And what I mean by that is, well, the literature suggests that the two models aren't necessarily mutually exclusive. And the court jester actually operates at larger scales than the Red Queen. And those scales are temporal, so in terms of time, but also geographical, so in terms of range size. So when you zoom out far enough, in terms of time, for example, you expect to see more of a role for the court jester. What I find quite strange about this is that if that's true, then we should be expecting the court jester, because my analysis that I showed before is for hominins as a whole. So that's, of course, a huge portion of, well, a large portion of Africa that I'm including, and a relatively long period of time. But you could, if you were the court jester, appeal again and say that there's another scaling issue at play here, and that's that the area might be too large. So you can imagine that if hominins live in different habitats, and those habitats respond differently to my measures of climate, and those responses essentially are in different directions, those effects will cancel each other out. But I'm a bit skeptical of that kind of argument, because I don't think any of the environmental reconstructions would have hominins living in vastly different habitats. But again, that's not really my area. So yeah, a little bit skeptical. But what I think is a good proxy for testing this kind of thing is to redo the analysis, but do it by genus. Because if we've assigned species to genera correctly, a genus should essentially align with an adaptive zone, so a kind of habitat zone. And so I did that. And again, the evidence for climate isn't really that strong. The only correlation I find is for the aeolian dust, where there's an effect for Australopithecus, in which when it gets drier, speciation slows down. But on balance, the evidence really isn't strong. And then when I do it for the Red Queen, species density is a really strong predictor of speciation rate in all of the hominin genera. So you can make yet another appeal and say that there's a problem of interactions. And the idea there is that even if species density is a more direct cause of speciation, climate might affect habitat, and habitat determines species distributions and density. So climate could be sort of 1 or 2 levels removed from speciation and have an effect in that sense. And so when I put all these variables together in a model for hominins as a whole, that's exactly what we see. So there is an interaction term that's significant. Now, what I interpret this to mean is that there is a role for climate in shaping hominin speciation, but it's an indirect one. So abiotic factors potentially shape species density, but the more immediate effect on speciation rate is species density. I think that summarizes it relatively well. So the overall idea here is that when you take these phylogenetic relationships into account and you directly measure speciation, abiotic factors may have played a role indirectly in shaping hominin speciation, but the more direct impact was probably, well, potentially had by other hominin species. I'm not trying to ruin everyone's life. I'm not trying to make the case that climate didn't have an impact on hominin macroevolution. Because I'm saying that, potentially it was a more indirect role than we've previously thought, but it could be that it affects extinction rather than speciation. And of course, extinction is a component of macroevolution. But the bottom line here is that I think biotic interactions have been underexplored in our field and should be explored a little bit more. And that's kind of what I want to do for the rest of this talk. So one of my favorite macroevolutionary processes, I never thought I'd say that, is radiations, whether or not they're adaptive. Now, radiations are inherently a Red Queenie type of process, because what you've got there is closely related species competing for the same kind of finite or constrained niche spaces. So essentially, they're controlling each other's macroevolutionary dynamics to some degree. And the obvious example is Darwin's finches here. That's an adaptive radiation. Now, if this type of competition, so this type of biotic interaction existed in hominins, we'd expect two patterns in the data. The first is that speciation rate should be time dependent and it should slow down over time. And hand in hand with that should go that density should be, well, density dependent speciation. And what we'd expect to see there is that speciation should slow down as a factor of increasing numbers of species. So basically, the more species, the slower speciation rate. The reason for that's fairly obvious. If all niches are occupied, you can't speciate into a new one. So there's kind of species are keeping checks and balances on each other's speciation. An important thing to note is that in most zoological literature, only time dependence is measured. And if you see negative time dependence, that's automatically taken or assumed to be the outcome of density dependent speciation. But I kind of want to challenge that a little bit by looking at this type of pattern in hominins. So really what I want to ask for the remainder of the talk is, do we see these patterns in hominins as well? Do we see this time dependent speciation, and do we see this density dependent speciation? And if you've been paying attention, you'll know the answer to, to the second one. But really, I want to know, what were these biotic interactions like in hominins? So quick note on methods here. I can't regress this tip dr, speciation rate, against time, because there's already a time component in a rate. So what I did instead was, this is a lineage through time plot, which it's important to realize this doesn't just show the number of species, but because ancestral species are included in this. So this is the whole history of the clade. But anyway, what I did was I used phylogenetic GLMs to compare speciation rate before and after the peak. The answer seems fairly obvious from this, but it actually isn't. It looks like speciation rate's slowing down after the peak, but it doesn't have to be this way. And the thing to remember here is that this graph essentially shows diversification, which means it includes extinction. So what could be happening after one of those peaks is that speciation rate is exactly the same. It's just that when species numbers start going down, extinction could be outpacing or increasing, and therefore outpacing speciation rate. But you might have a situation in which a random species after the peak actually has the same chance of speciating as it did before the peak. It's just that extinction is happening at a higher rate after the peak. So I think this is another kind of benefit of using phylogenies. You can single out one of those processes and actually examine it in more detail. For hominins as a whole, there's no relationship between speciation rate and time. So speciation rate after the 2 million year mark, which is kind of the peak, the heyday of hominin diversity, the lineages still had the same kind of chance of speciating as they did before the peak. And I think that's really, really interesting because you see that you don't see this kind of pattern in many other clades. In fact, what you see, as I've kind of alluded to, is negative time dependence. And you see this in other mammals, you see it in birds, you see it in reptiles, marine clades. And the implication for me is that hominins as a whole, when we take the lineage as a whole, never actually reached carrying capacity. So that might go some way to explain why the lineage as a whole was so comparatively rich in species compared to other fossil lineages. Now, what is going on there? I think it's the genera are basically just replacing each other. So when you separate the data by genus, speciation is inversely related to time. So you've got this slowing down of speciation rate over time. So within these genera, you do see the pattern you expect. But overall, these genera kind of replace each other. They overlap in space and time and they replace each other. And the net effect of all of that is that those effects cancel each other out. And so we get this almost constant speciation rate. Right, now density dependence, as you'll no doubt remember, speciation rate is somewhat inversely related, or it's negatively related to species density for hominins as a whole, which is the expected pattern. But what's unexpected is this constant rate through time. So that's kind of the first questionable element of the paradigm in other zoological studies, that negative time-dependent speciation should always go hand in hand with negative density-dependent speciation. So that clearly isn't always the case. Hominins are strange, but yeah, it's not a universal. Then when we separate the data into the three genera, Australopithecus and Paranthropus show the pattern we expect, so negative density-dependent speciation, and then Homo does something completely different and completely unexpected. For Homo, speciation rate is positively related to the number of species already present. So that means that in Homo, the more species, the higher speciation rate. This really should feel like a horrifying slide, but it's okay because it's nearly Halloween. Well, it's horrifying because it really is a nail in the coffin of this existing paradigm, because in Homo we did have this slowdown of speciation over time, but then we also see a positive relationship between the number of species and speciation. So the point here is that we should reassess the kind of blind assumption that negative time dependence is always because of negative density dependence. Question, of course, is why? And the time we're interested in is this period of turnover around 2 million years ago. Two patterns to be noticed. The first is the decreasing species richness in Australopithecus and Paranthropus. And we know that this is to some degree due to decreasing speciation rates. And of course, the second pattern is this increase in the number of species of Homo, which we now also know is the result of higher speciation rates. So there's two potential classes of explanations. The first is that Australopithecus and Paranthropus are, in a sense, outpaced by a changing environment. What you'd expect to see there is that they can't speciate in the time that they have to respond to a changing environment. And then if there's also an element of extinction happening because of the environment, Homo can speciate into those empty niches. Or it could be a case that Homo actively competes with Australopithecus and Paranthropus to almost directly take over their niches. Now, of course, luckily we've done the first analysis, and remember, only aeolian dust correlated with speciation rate in Australopithecus, and that does explain the decrease in speciation rate that we see around 2 million years ago, or a little bit earlier for Australopithecus. Again, it's important to remember that I'm not saying anything about extinction. So it could be the case, as I've mentioned, that Homo starts to occupy emptied niches due to extinction also increasing for Australopithecus. But I think altogether the evidence for a direct cause or direct causal relationship between this slowdown in speciation rate and climate is a little bit weak. And the impact of climate on Homo is, as I've mentioned before, still only indirect. And for Homo, at least, it seems that species themselves are having more of an effect. So maybe it could be the case that the presence of those other species is a selective pressure in and of itself, and Homo responds to this kind of pressure by either creating new niches or outcompeting Australopithecus and Paranthropus for the same niches. Now, one way it could have potentially done that is through lithics. You can imagine that if you have stone tool technology, you can actively make available new niche space, or you can potentially occupy the same niche just more efficiently than other species. The way forward for me is going to be to test this in more detail. I found my data a bit too crude for my liking at the moment, because I was using just stone tool modes, and I think a better approach is going to be to quantify the niches directly and include them in a phylogenetic model to actually distinguish between Homo competing for the same niches or creating new niches. But we're going to have to disentangle these in the future, I think. To sort of summarize this section, it's all early days, as I said, a bit of a wild west. But I think a fair summary of this section is that biotic interactions between hominin species, and specifically how those interactions shaped patterns of speciation, deserve a lot more research attention. And Homo overall does seem to be a really odd genus, macroevolutionarily speaking. And that's odd compared to a lot of other mammals, birds, as I said, reptiles, marine clades, and of course, Australopithecus and Paranthropus. So to kind of come back to the original slide, I think phylogenies should be used as a source of data rather than an end in and of itself. And overall, the results of reassessing old questions using this kind of data can be quite unexpected. I think of this approach as complementary to what's already being done. Also, I don't want to preach gospel and kind of say this is the be all end all. I think it sort of, my results kind of point us in a new research direction that we can explore in more detail. Because this Red Queen effect seems, using this kind of data at least, to be the kind of intermediary between environmental factors and hominin speciation. But yeah, thank you so much. Obviously to my supervisor, Rob, also Luke Harmon, who advised me on the phylogenetic component of the regressions that I did. And of course to Sophie for organizing this. I know it's an awful lot of work to organize the seminar series. I've done it myself, and it takes up a lot of time. And yeah, thank you so much. And thank you to everyone for listening.
Thank you, Laura, for such a fantastic talk. It was incredibly interesting. You can breathe now. So we've got lots of questions now. Or... Oh no, you can keep
going. Okay.
So we've got some questions, so I think I'll just dive straight in. So the first question is, do you assume that robustus groups with Boisei and Aeopithecus, or do you also consider the possibility of convergent evolution of robustus?
Wait, can you say that?
Yeah, sorry, I am terrible with the names. Do you assume that robustus groups with Boisei and Aethiopicus, or do you also consider the possibility of convergent evolution of robustus?
So I didn't make that phylogeny, so I didn't. I don't have much to say in response to that question, because this approach is more about the sort of speciation rates rather than the direction that traits are themselves evolving in. So I find that a little bit difficult to answer, actually. I'm not sure. Yeah.
Great, thank you. Next question. Has this been done for any other branches of primates? And if so, what were the findings? Is there any reason to think we might see similar trends across the order?
I think, yeah, so this is something that I actually want to do. The thing about this approach, of course, is that I'm using a fossil tree, or a tree with fossils included. And I was looking for good, relatively well-resolved phylogenies of fossil primates, because I want to include the fossils to actually compare accurately with hominins. And I couldn't find ones, first of all, with sufficient species. So no, it's not been done for primates, especially not taking fossils into account. The issue there, of course, is that the hominin fossil record is relatively good. I mean, I sometimes lament the lack of data, or, my other paper was about all mammals, so I had a lot more data points to work with. But actually, the human fossil record was comparatively rich, and we just don't have as many fossils for the other primate clades. But yeah, I would want to do this for primates as a whole, but including fossil data.
Thank you. So the next question is, Mongol et al. Estimates that approximately 40% of the characters of Dembo et al.'s matrix are redundant. Do you consider how this might affect topology and hence your analyses?
Yeah, so as I meant, I didn't mention it in much detail, but well, first of all, I agree, and that there are actually some elements of that phylogeny, and also the parents one that I sort of, out of the two would kind of place my money on. There are some elements of the topology that I don't think, if you're more of a fossil kind of person and you come at it from that kind of perspective, you'd agree with. So the reason really that Rob and I are making this sort of consensus phylogeny to redo all of these analyses on is basically for that reason. As I've kind of mentioned, the point of the PhD wasn't to make a new phylogeny. It's just exploring how phylogenies can be used. So my primary concern wasn't really the specifics of the Dembo phylogeny, but I do agree that there are some elements of it that could be improved upon, and and we're trying to address that with that phylogeny that we're making. Yeah.
Thank you. Okay, the next question is, species density is a strong predictor of speciation rate, but climate change should affect species density, affecting the carrying capacity of an ecosystem. Do you consider this in your models?
Yeah, so that's actually what I showed. And that's the kind of point of the interaction model. I don't know if I can go back. No. Oh, I can go back all the way to. Yeah, so that was kind of the conclusion of this bit of the presentation, that of course these things aren't mutually exclusive, and there's an interaction effect there.
Thank you. Do you consider pseudo-extinction? A species of Australopithecus evolved into a species of Homo, and the taxonomic distinction of the genus level may be an artifact of taxonomy.
Yeah, and again, you'd kind of want to rerun this kind of analysis on multiple phylogenies to sort of take into account this kind of phylogenetic uncertainty. We're limited, and I kind of mentioned this. We're limited in the number of phylogenies that there are. I don't actively consider pseudo extinction in my models, no. But I agree that there's phylogenetic uncertainty, and we should be basically running the analysis multiple times on different topologies.
Thank you. Are there differences in speciation rates if comparing slices before and after the advent of stone tools?
I haven't actually done that. In a sense, I guess I do it in this kind of approach, where for Homo, I didn't actually put the lineage through time plot for Homo here, but in a sense, I'm comparing for Homo the speciation rate before the peak and after the peak, and that peak is roughly when stone tools first appear. It's I don't actively test it, but I guess I sort of test it in that. And as you remember here, speciation rate for Homo actually does slow down after stone tools appear. So I've not directly tested this, but indirectly, I guess I have.
What data, including fossil and modern ecological data, would be critical to collect to help answer these questions?
I think, well, it would always be nice to. I mean, you'd never be quite sure, but it would be nice to know that we'd found all hominins, so we can, be sure that the topology of the trees that we're using is completely accurate. I think also, the Dembo data set includes only cranial data, so both these phylogenies are based on cranial data. I think there's a paper by Wood, I think it's Wood and Collard, that kind of show that cranial metrics really aren't that great, and actually, cranial metrics aren't really that good at reconstructing the primate phylogeny. So we'd want to, as I said, find more fossils, but also include different types, so postcranial data, and then of course make a mixed evidence phylogeny with the genetic data. Be nice to sequence more hominins. And then in terms of ecological data, I'd really want to look at primates more generally, and look at kind of, I think it was one of the first two questions, do this kind of thing for primates and see whether you get this kind of replacement of different genera, but also, yeah, basically just redo the whole thing with primates for which we know the ecological data a little bit better.
Thank you. Another question is, tectonics in Eastern Africa may be a key external/abiotic factor in promoting speciation and extinction. Could this be considered in your models?
Yeah, absolutely. So, well, I probably should have said so, but you know, you can use this kind of approach with any kind of data, really, and I could definitely, yeah, use that kind of data, basically rerun the analyses and see what comes out.
Thank you. A lot of people are saying great talk, and thank you very much.
Thanks.
Then I've got a question saying, how much of these analyses biased by selection of data set? For example, picking a lumper versus a splitter topology.
So I've not, clearly I've not directly tested that because I just use these phylogenies that are already in existence. I think if we go, well, I can't go back for some reason, but the phylogenies themselves split Homo erectus into 3 groups. So I could rerun, and in fact, I was doing that yesterday, but I haven't got the results of that yet. Rerun the analysis with, for example, Homo erectus as being one group. But yeah, so as mentioned, I mean, I'm trying out this approach on phylogenies that already exist. So I'm in a sense, I'm bounded by their philosophy.
Thank you. Might there be different patterns in African hominins versus Eurasian hominins?
Yeah, I think range would be something to include in models. And in fact, I'm planning on including range in the models and seeing how range size potentially how range size affects speciation, but also doing this redoing the analyses by region rather than by genus, for example. I imagine so. I mean, I'm not sure to what extent this is, biased by the amount of time we've spent excavating Africa relative to other areas. But in Africa, there are more species, so there is more of a role potentially for red queenie type dynamics, and therefore, if other species are having an effect on speciation rate, for that to come across in the data. Whereas in Eurasia, species tend to be more spread out and there's fewer, so perhaps there's less of a potential role, and speciation rate would then be a factor. So yeah, I think so.
Thank you. What was the role of subspecies in your model?
It's not included here.
Do you think it would play any role?
Well, one way in which you could expect speciation rate to have a negative correlation with time if and you would erroneously pick that up if subspecies, or if I guess if species were speciating or were kind of in between the stage of subspeciation and speciation, and we weren't counting that kind of in-between stage as a species, because then it would look like there's fewer species than there actually are. But that would really only affect, yeah, it depends on, can we recognize subspecies in fossils? I'm not too sure. But yeah, I didn't use them, so there was no role for them.
Have you looked at these trends in other fauna?
No.
No. Okay.
So, very quick answer.
Very quick answer, yeah. Well, if anyone else has any more questions, please feel free to write them in the chat. But thank you very much, Laura. It's been really brilliant having you.
I really enjoyed.
Sorry, there's just another question. It's just popped through. What's the next step? What would you do next to strengthen your conclusions?
So really, for me, it's going to be the quality of the phylogeny. And by quality, I mean, I want to, so the sort of, we're calling it the consensus phylogeny. But what we're really doing is, the old kind of approach of making big phylogenies, super trees, is basically stitching together cladograms or phylogenies and putting a time element in. And those cladograms tend to be based on kind of more expert opinions on relationships between species, stitching them all together and kind of making something that I think more people would agree with. And essentially that would also be based on more kinds of data. So yeah, it's going to be the phylogeny. So I want to rerun this whole thing on a slightly more consensus phylogeny, really, to see if the results hold up, essentially, or if the patterns still appear.
Are you considering any additional abiotic variables in your future models?
Yeah, I could consider a lot. For me, it was, I kind of have to stop myself because I have a lot of things that I want to test with this kind of approach. I had to stop myself because otherwise the paper would get a little bit too big and the presentation would be too long. So the abiotic element actually was a relatively recent addition to my thinking, because the first kind of trial run of this was just to look at the density dependence of the speciation. And then I framed it in the Red Queen Court Jester kind of model. But yeah, I definitely want to look at some other abiotic factors. I mean, I don't know who asked the question, but the tectonic dynamics would be one to include. Yeah, perhaps, I mean, things like more indirect measures of things like temperature. Yeah, these kinds of things.
Thank you. So I think that's all the questions we've currently received. So I may wait one more second to see if anything more comes in.
Yeah, sure.
But yes, thank you so much for such a fantastic talk. It was really interesting.
Well, thank you for hosting.
To finally have you, because you were due in March and then have been postponed a couple of times.
That's all right. Yeah, thank you so much for having me.
Yeah, well, hopefully it can be an in-person talk soon.
Yeah, with more models and perhaps new phylogenies.
Exactly. Well, I think that's all the questions for now. So thank you very much, everyone, for tuning in, and looking forward to welcoming you again next week for another Primate conversation.